In this video, we move on to chapter 6, and we start off with section 6.1, which is all about power series. So what is a power series? In the most simplest terms, a power series is a type of series whose terms involve a variable. Right, so for example, the series, the sum from 1 to infinity, 0 to infinity actually, of x to the n, right, which is x to the 0, which is 1, x to the 1, which is x, and then x squared, x cubed, right, so on and so forth. We get to x to 100, and we go on forever and ever. And, right, so now we see, right, this technically here is x to the 0. So in this type of series, right, all of, right, so if 1, then all of the terms of the series involve powers of x. And then, right, when we look at this right hand side of this series, right, we can see that this is actually a polynomial, right? Remember, polynomial is an equation with powers of x, so this here is an infinite polynomial. So notice that a power series can be thought of as an infinite polynomial. Okay, so this is our very crude introduction into power series, and now I will formally define a power series. So the definition is that a series of the form the sum from 0 to infinity of some equation, some formula, Cn, right? Cn is like the formula for the sequence, times x to the n. Right, so when you plug in 0, that's C0, x0, plus when we plug in 1, that's C1, x1, plus C2, x2, and so on and so forth. And this is a power series centered at 0. And this term centered will make more sense later on as we continue to discuss this section. Basically, we're going to see that power series converge for certain values of x and may not converge for others. And the center is the center of the interval where it does converge. So then a series of the form the sum from 0 to infinity, 0 to infinity of, again, our formula Cn times, this time we subtract a from the x, right? So the first few terms is C0, and then that's x minus a all to the 0 power, so that goes to 1. And then C1, x minus a to the first power. And then C2, and then x minus a to the second power. And so on and so forth. So make sure you don't confuse the a and the n. Okay. And this is a power series now, right, we used to have nothing subtracted from the x, so you could technically think about this as x minus 0. Let me write that in another color. So this is a power series centered at x equals a. So a is going to be some number. Okay, so there's two kinds of power series, right? Technically it's all one kind, but it's just that the center is either 0 or non-zero, right? And so either you're going to see the a explicitly written right there, the non-zero, or you're going to see an imaginary 0 that we don't bother writing because that would be a waste of our time. So let's look at this notation, look at some examples. Right, so let's look at the series from 0 to infinity of x to n over n factorial. Right, the first term, right, is x to the 0, which is 1, over 0 factorial, which is also 1. And then the second term is x to the 1 over 1 factorial, which is also just 1, so that's just x. And then x to the 2 over 2 factorial, plus x to the 3 over 3 factorial, and so on and so forth. Right, so the first question is where is it centered, and the second question is what's the Cn, right? So here we don't see, when we look at the x to the power of n, we don't see nothing subtracted from the x, so therefore we know that this is a power series. Oops, little typo there. Power series centered at 0. And then, for example, if we were given, and then what's the Cn, right? Well, notice we can look at this as the sum from 0 to infinity, right? And the Cn is everything other than the x to the n or the x minus a to the n. So we can look at this as if we pull down the x to the n, that would be x to the n times 1 over n factorial. So then our Cn here in this case is equals to 1 over n factorial. Right. Okay. And then another example, right? If we were given the series, the sum from 0 to infinity of x minus 2 to the n all over n plus 1 times 3 to the n. Right, now we see that for our x to the power of n, we do have a constant being subtracted, right? We have that minus 2 there. So this means that this is a power series centered at 2, right? So whatever you subtract from the x is the center, right? If you added something, that means it would be negative center. And when we say at 2, like, right, we're referring to x values, right? Because basically what we're saying is when we plug in 2, all of our terms are going to be 0 because it's going to be 2 minus 2, right? Same thing here. When we plug in 0 into x, right, all of the x becomes 0. So, okay. And then here, right, we can rewrite this, how we see this sum, by pulling down the numerator, and then what's left is the denominator, n plus 1 times 3 to the n. So our Cn is just that, 1 over n plus 1 times 3 to the n. Okay, so hopefully that notation and that definition all makes sense to you. Now let's talk about, when does a power series converge, and I hinted at this earlier in the video, right, that the convergence now, because we have an x term, well, x's inner terms, it's going to be just a little bit more complex because convergence is now going to depend on the values of x. So since the terms in a power series involve a variable x, the series may converge for certain values of x and diverge for other values of x. Alright, so let's talk about the three cases that you can get for convergence of a power series. So I guess we can call this a theorem, right? This is a fact, a rule that we obey. So consider the power series. And most generically, our power series is a power series centered at A, because remember, we can make A be 0 or we can make it be something else, right? So even with a 0, this is the form for a power series. Then the series satisfies exactly one of the following. The first possibility is that the series converges at the center, right, the center, and diverges everywhere else. Right, so for all of the x not equal to A. And in this case, right, so we say, so the reason why we call A the center is because that's the center of our interval of convergence, which I'll talk about later. Right, so in this first case, the center is A and that's the only place where it converges. So our radius of convergence, right, how far we go from the center out of the interval of convergence is 0, right, because we only stay at that one point. So then that'll make sense later. The second option is that the series converges everywhere. So for all real numbers x, and here we say that the radius of convergence is infinite. And then the last part is that you have some subinterval. So then there is a real number, capital R, which stands for the radius of convergence, such that the series converges if the absolute value of x minus A is less than R, and diverges at the absolute value of x minus A greater than R. And then when it's equal to R, you have to double check and figure out whether it converges or diverges. So you have to plug in that x value. So solve for x and then plug that in. So at those values, it may converge or diverge. Check. That is your job to check. Okay, so right, so here in this last case, right, the set of values well, it's all the interval of convergence, but technically in 1 it's only a point, and technically in 2 it's the whole number line. So in 3 is where we get like actual interval. But so the set of values x, for which the series converges is known as the interval of convergence. So interval of convergence, I've been saying it, but that is one of our vocabulary words. And as I've been calling capital R, right, the value of R is called the radius of convergence. Oops. And I already told you, right, in case number 1, when you only converge at x equals a, then R is 0. And in case number 2, where you converge for all real numbers, your R is infinity. In case number 3, your R is going to be, right, some finite number. So let's do at least one example in this video, and then I think I'll end it and do a couple examples in a follow-up video. So in this example, we're going to find for the following series, find the interval and radius of convergence. So the series we're given is the sum from 0 to infinity of x to the n over n factorial. Right, so basically what we always have to do is we just check for convergence like we normally would. So the first thing is to check for convergence, and because this series has an exponential and a factorial, I know that I should use the ratio test. Right, so remember the ratio test is that we calculate rho by the limit of the ratio of two consecutive terms, and then depending on that value we get divergence. So in this case, right, we have an, right, is our x to the n over n factorial, so that makes an plus 1, right, we replace the n with n plus 1, like that. So then rho is equals to the limit as n approaches infinity. An plus 1 is in the numerator, and then we have a n in the denominator. And then, right, we can't divide by fractions, so we keep the numerator as is, which is x to the n plus 1 over n plus 1 factorial, and change the division to multiplication and flip the denominator, right? So we're using keep, change, flip. Right, and now we're going to rewrite things so that we can see that things cancel out as we were doing in the last section 5.6, right? So x to the n plus 1, we use rules of exponents, and we know that's x to the n times x to the 1, and then we have n factorial, and then n plus 1 factorial we know is all of the first n terms times n plus 1, and then we have x to the n to bring over. Right, so then we see, because all of this is being multiplied, if we multiply by xn, divide by xn, those cancel. Multiply by n factorial, divide by n factorial, those are gone. Right, so then what's left in my limit is x over n plus 1. right? And here, remember, limits, we can pull constants out, right? They have linearity, so we can pull out the absolute value of x because we know that's going to stay positive, and then we know this 1 over n plus 1 is positive by default, because n, remember, we established is going from 0 to infinity, so it's always positive. Right, and then we know that this limit here, right, is going to 0 because n is in the denominator, so this whole thing is going to 0 because x times 0 is 0, right? Anything times 0 is 0. So our rho is 0, which, remember, when rho is less than 1, the ratio test says the series converges. Right, and now this rho doesn't depend on x. If it depended on x, we would have to see for what x is it less than 1 and for what x is it greater than 1. But here, right, this is true for all x. So therefore, right, the series converges for all values of x. Therefore, the interval of convergence, right, is the whole entire number line. So that means that our radius of, right, the center of this series is 0 and its radius is infinity because it goes infinity out to the right and infinity out to the left to negative infinity. So the radius of convergence is r equals infinity. And if we look at the formula for our series, we see that the center, right, the center is 0. Right, so what is that? That is that when we think about our interval of convergence, the center of our interval of convergence is 0. Right, and in this case, we go off to the right infinity and to the left negative infinity. So this whole thing is our interval of convergence. Right, and then from the center, we go to the left radius and to the right the radius. All right, and I'll do more examples in a follow-up video later. Thank you.